All right, YouTube, we're back. And what did we do today? What is a vector cross product? Oh, let's talk about this. Remember that 2 dot 3 is 6 and 2 cross 3 is 6, but they're only the same operation, dot product and cross product, when you're dealing with scalars or numbers. So today we're going to talk about how they're different, the dot product and the cross product for vectors. All right, so let's go straight to the homework page. The homework is page 629 multiples of 10. So let's take a look at something from that page. How about 39? Now, 39 is actually a review. It says, what if V is a vector in 3 dimensions with a delta x of 1, a delta y of 2, and a delta z of 3. And W is likewise -2, 3, 0. All right, how do you add the vectors? Remember, you add them component-wise. You just add your delta x's, your delta y's, and your delta z's. But how do you subtract them? Remember, you never do. How do you subtract? You add the opposite. So what is the opposite of W? It's V plus the opposite of W. Well, the opposite of W is the same as distributing -1 over here. So you get 2, -3, 0. So let's add V and -W, and don't you get, let's see, 3, -1, and 3. Okay, good. So that's not new. And also multiplying by a scalar like -1, that's not new. What about V dot W? Well, Cartesian-wise, it's delta x times delta x plus delta y, plus delta y times delta y plus delta z times delta z. So take a look at your V's and W's. Delta x times delta x plus delta y times delta y plus delta z times delta z. And so you get -2 plus 6 plus 0 is 4. All right, that's if you do it Cartesian-wise, using x's and y's and z's. What if you do it polar-wise? Remember, there's another way. There's another way to do the dot product polar-wise, remember? It's V dot W can also be calculated as the magnitude of V times the magnitude of W times the cosine of the angle between the two vectors if you graph them both at the same starting point or tail to tail. All right, so V dot W, we just figured out it's 4. What's the magnitude of V? Well, square it, add it, square it. So 1 plus 4 plus 9 is 14, rad 14. And how about the length of W? Square it, add it, square it. So 4 plus 9 plus 0 is 13. So rad 13, just Pythagoras in 3D. And so you get that 4 equals rad 14, rad 13, cosine of theta. So how do you get theta alone? Well, let's get cosine first alone. Divide by rad 14, rad 13, and you get 4 over rad 14, rad 13 is the cosine of theta. So theta is the second cosine on your calculator, or the inverse cosine of 4 over rad 14, rad 13. Whoops. Rad 14, rad 13. And that's not a reference angle. That's not a cosine that we know from the unit circle, right? So let's figure it out on the calculator. Let's see if I have a calculator open. I don't. All right, so let me open the calculator. Hang on. Where is my calculator? Okay. Let's go to the desktop. Let's go to Wabbit. There you go. All right, come on. And, well, it looks like it did it here already, but let's start over. View, large screen, LCD. There you go. All right, so if I'm in degree mode, I want degrees for today for some reason. You don't have to do degree mode, but second cosine. Now, how about this? Alpha y equals 1 of 4 over rad 14, get out of the rad, times rad 13 in the denominator, get out of the rad, get out of the arc cosine, and you get 72.753 degrees. Some people got stuck with this, not using the rational key, so you could do this, second cosine of 4 divided by the quantity, rad 14, times rad 13. Get out of the radical, get out of the denominator, get out of the arc cosine, same thing. I do this though a lot. Inverse cosine of 4 divided by rad 14, get out of the rad, also divided by rad 13, get out of the rad, close the arc cosine, same thing. Any one of those ways is fine. All right, so 72.753 degrees roughly. Let's write that. So theta is exactly the arc cosine of 4 over rad 14 over rad 13, but it's approximately, remember dot equals, if you're approximating, 72.753. And don't forget, if you're doing degrees, to say so. Alrighty, so that was pretty much review of 904, screencast 904, 905, 906. Here's what's new. How do you do a dot product? I'm sorry, cross product. And what does that mean? Okay, here we go. Number 9 on page 629 says, all right, V is 2 in the I direction minus 3 in the J direction plus 1 in the K direction. In other words, delta X is 2, delta Y is negative 3, and delta Z is 1. And W is 3 in the I direction minus 2 in the J direction minus K in the minus 1 in the K directions. In other words, delta X is 3, delta Y is negative 2, and delta Z is negative 1. So how do you do a cross product? This is how it goes. V cross W is the determinant or absolute value of a 3 by 3 matrix. Now, what's a matrix? A matrix is like, right? I mean, consider this vector. This is a vector of numbers, 3, negative 2, and negative 1. But consider a vector made up of vectors. Instead of 3, there's another vector. Say a column vector. This is called a row vector, what I circled, right? So you put a column vector in place of 3, and a column vector in place of negative 2, and a column vector in place of negative 1. You get what's called a matrix. This is chapter 11. We didn't do chapter 11 yet, but I got to show you one little thing from chapter 11. How do you get the determinant or absolute value of a 3 by 3 matrix? And how do you set up the cross product? The cross product, let's set it up this way. It's the absolute value, right? The first row is IJK. The second row is V. So 2, negative 3, 1. Be careful, the order is going to matter. You're going to find that V cross W is not usually the same as W cross V, as opposed to V dot W is the same as W dot V. And another difference is dot product gives you a number, cross product is going to give you a new vector. And what goes in the third row? 3, negative 2, negative 1. All right, so how do you evaluate this? To evaluate this, you end up with another vector, orthogonal to V and W. In other words, perpendicular to both of them, the plane, perpendicular to the plane where V and W live. And so it goes like this. V cross W is equal to a certain number of I's minus a certain number of J's plus a certain number of K's. Now what you do is the IJK's are taken care of. Forget that for now. To get the coefficient in front of the I unit vector, cover up the I column and do the, look at the numbers you have left here, this little negative 3, 1, negative 2, negative 1, right? You take the main diagonal, negative 3, negative 1, multiply that, that's the product of the main diagonal, minus the product of the minor diagonal, which is 1 times negative 2. So negative 3 times negative 1 is 3, minus 1 times negative 2 is negative 2. All right, how do you do the J coefficient? Well, there's a negative there already, and then what goes into parentheses? Well, ignore the J column, cover it up, and now it's 2 times negative 1, which is negative 2, minus 1 times 3, which is 3. Okay. And then how do you do the K coefficient? The K coefficient is cover up the K column, and you get negative 4 minus negative 9. Okay. So how do you subtract minus a negative 2? You really don't. You add a positive 2, so you get 5 in the I direction. What's negative 2 minus 3, or negative 2 plus a negative 3 is negative 5, but I'm subtracting negative 5, so plus J. And how do you subtract the negative 9? You're really adding a positive 9. What's a 9 plus a negative 4? It's also 5. As it turns out, all three coefficients, I, J, K's coefficients, are all the same in this case. Doesn't have to be. And so, that's your answer, a new vector. Now, if you were to graph this, we're probably going to do this on Friday, graphing in Sage, you're going to see that this vector is perpendicular to the other two, to V and W. All right, but look at this. The magnitude of this vector is equal to the magnitude of V times the magnitude of W, sort of like the polar form of dot product, but times the sine of the angle between the two vectors. That's interesting. So can we figure out the angle between these two vectors? Well, what's the magnitude of v cross w? Square it, square it, square it, add it, square it. So 25 plus 25 plus 25 is 75. So this is rad 75. And then what's the length of v? Well, square it, square it, square it, add it, square it. 4 plus 9 plus 1 is rad 14. Okay. And the same thing for w. Square it, square it, square it, add it, square it. So 9 plus 4 plus 1 is again 14, so rad 14. Sine of theta. So how do you get theta? Well, get rid of the rad 14s. By the way, rad 14 times rad 14 is just 14. So divide by 14. Whoops. Rad 75 over 14 is the sine of theta. So theta is the inverse sine, or the second sine on your calculator, or the arc sine of rad 75 over 14. So theta is approximately, well, let's use the calculator. So instead of inverse cosine, it's inverse sine, and it's rad 75 over 14. Okay. So where's my calculator? So, clear all of this. So second sine of rad 75, get out of the rad, divided by 14, and you get 38.213 degrees. So let's write that. Approximately, remember the dot equals if you're rounding off. 38. Whoops, I wrote it wrong. Let me go. 38.22. Why am I doing this? 213 degrees. There you go. All right, but look at this. Not only is the new vector 5, 5, 5. By the way, you could write it that way, right? Delta x is 5, delta y is 5, delta z is 5, right? Not only is it perpendicular to the other two vectors, and it's used in physics for something called torque, like the dot product is used in physics to measure work. There's another interesting result here. The magnitude of v cross w, because v cross w is a vector, right? The magnitude of the vector is a number, is the length of v times the length of w times the sine of the angle in between. But doesn't that sound familiar? Look at this. K equals 1/2 AB sine C. What was that? That was the angle of that was the area of a triangle, where you know the length of two adjacent sides. A and B are the lengths, right? And C is the angle in between. The only difference, see, the magnitude of V is the length of a side. The magnitude of W is like the main length of a side. If you think of two vectors, remember the law of the parallelogram? When you add two vectors, the resultant vector is the diagonal of the parallelogram. Well, think of half of that parallelogram as a triangle. This is the area of that triangle. So, if K is 1/2 that, the magnitude of the cross product vector, this thing, is twice the area of one single triangle. So it's a whole parallelogram. That's the area of the parallelogram defined by the law of the parallelograms, by the two vectors if you put them tail to tail. Isn't that interesting? Alrighty, so let's see. I think that's everything we did today in class. So let's save that. I think we're going to stop with that. Okay, that's good for today, YouTube. Have fun. Enjoy.